Good morning, ladies and gentlemen. My name is Mike Batty. I'm Bartlett Professor of Planning at University College London. And I'm here to speak with our participants about urban science. And I will particularly be concentrating on ideal cities and complex systems. Let me say a few words before I begin. What you're seeing here is a recording of my Zoom talk. I'm not able to be present with you virtually, if that's not a contradiction in terms, largely because it's 2 a.m. in the morning here in London when you hear this. And I thought it would probably be a little bit better for me to record it. You get a better rendition of what I have to say, rather than me getting up at 2 a.m. and trying to deliver it at that particular point. Okay, so ideal cities and complex systems. Let me also say that if you want a copy of this talk, then if you look at one of the web addresses here, the top web address is my blog, and the bottom web address, it's the same one. It's a tiny URL, it's a shortened one, tinyurl.com, YHRSU4A3. A little bit of a mouthful, I know, but take a photograph of it if you want to see the PDF either during or after the presentation. Okay, without more ado, let me begin and tell you what I'm going to talk about. Okay, several topics here. I want to begin by talking a little bit about a theory of cities. We need to think about the theoretical context in which we sit in this sense, but also the second point is that we need to think about the physical planning of the city. So to some extent, a good deal, if not most of what we're talking about is related to physical planning. Those are the instruments that change our cities for the better, hopefully. And I really want to sort of dwell a little bit on this in a sense, because clearly this presents a dilemma to some extent in that it's much more difficult to think about social and economic and related forms of planning in this context. I also want to talk about ideal and real cities. I'm going to make this contrast between the ideal city, the city of vision, the architect's visionary city, and a real city in some sense. And those are poles apart in many ways, but they can be considered to be important in terms of what we're talking about in terms of a science of cities. I'll talk a little bit about rudimentary models of city systems. I say rudimentary because much of our theory is fairly primitive at the present state and is getting better to some extent. That's what the Urban Science Symposium is all about. But to some extent, they'll always remain rather basic, I think. I'll talk about the systems approach and complexity theory, and then I'll concentrate on this notion why ideal cities don't work and will never work, but why we need them in that sense. So the city of tomorrow, that's Le Corbusier's plan for Paris in 1924. The new towns, the British new towns, for example, are archetypal examples of visionary cities. And more recently, Neom, which is the linear city in Saudi Arabia, which in some sense is both outrageous and interesting. I'll talk a little bit about complexity to explore real cities, and then I'll finish very quickly talking about the idea of many models of the same system, many models of the same place in that sense. Also the same place, throwing up many models. These are effectively being called digital twins in the modern information technology parlance. And then I'll make the point that the future of digital world will be composed of many of these twins, many of these models. Okay, so what you're going to find too is that I've got to keep the talk within 20 minutes. It's probably going about 3 minutes at the moment, 20 minutes. Or 25 minutes maybe. I'll beg a little bit extra time from our hosts, basically, because I won't really be present, I don't think, in the discussion in some sense, although I may actually key in some answers to questions. Okay, let me begin then. Towards the theory of cities. Now, cities since prehistory have been articulated in terms of their physical form, what they look like. And any theory, insofar as it's ever been a theory, must therefore be rather superficial. It deals first and foremost with form, and then it digs down into function. Theory did slowly emerge in terms of cities from the Renaissance onwards, the Renaissance in Europe, that is, from Leonardo's time in that sense. And as the Industrial Revolution began and progressed through the mid-19th century, there were various theories put forward about how people and were people located in cities. In particular, the development of location theory in the 19th century from von Thunen onwards, who produced a simple economic model of the price of land and agglomeration. From von Thunen onwards and the German location theorists who followed up on his work, this represented the most formal aspects of thinking about cities then. There were also speculations in the 19th century that the Newtonian world of the 17th and 18th might also be a world of cities in some sense, that we could apply ideas of mass and force and gravitation and so on to cities. And that, in fact, has still found favor, and we're still doing that kind of thing in some senses. So there were speculations about a theory of cities in that sense. But generally speaking, most of our thinking about cities until fairly recently has been how they looked, and most of our planning has been to make them look better and to function better in a sense. So the ideal city, if you like, has crowded out to some extent the real city. Let me illustrate some of these ideas and begin just showing you location theory and then the visionary cities. Here's a picture of von Thunen and his model of the city. It's very resonant to a good deal of how we think about cities. If you take a bird's eye view of a city, you can see the concentric rings of land use, which normally are organized around the pole of the city, which is the traditional CBD. I know we have polycentric cities now with many CBDs and so on, or rather not many, but more than one in some senses. And in some senses, you can see all of von Thunen's theory encapsulated in this little diagram. Basically, you can see the impact of the river and how it distorts the transportation surface, how it changes costs in that sense. So that's really von Thunen, and his ideas were taken forward from the early 19th century through to the mid-20th in the form of urban economics, which to some extent in the year 1970 was really the pinnacle, if you like, of urban science back then. In contrast, Corbusier basically produced many visionary cities, but this is his plan for Paris in his book, The City of Tomorrow, in 1924. Again, fairly outrageous, a little bit like NEOM, I suppose, in Saudi Arabia. It's outrageous in the sense of thinking about central Paris being occupied by these blocks. But of course, Corb was making a point. He was making the point about compactness, sprawl, modernism, clean lines, and order in some sense. So it was really an expression of the modern movement. It was more a work of art, basically, than a workable hypothesis for a city in this sense. Okay, I suppose the only theoretical perspective that emerged in the 19th century was from Patrick Geddes, the so-called father of town planning, who really picked up on Darwin's ideas, and in his book published ultimately in 1915, Cities in Evolution, he argued that we should take the Darwinian model and that cities really should be thought about as evolving from the bottom up. This is very resonant, of course, with complexity theory, which is a very strong theme in urban science, basically. It was picked up, Geddes' ideas, they remained pretty dormant, basically, apart from lip service to them, until really the middle of the 20th century, when Jane Jacobs picked them up, or picked up the idea, I should say, of cities in evolution, the idea of evolving cities, in her book, The Death and Life of Great American Cities, where she talked about the idea that planning should be developed from the bottom up. In fact, she was no friend of Patrick Geddes, as you'd find from her writing. So your homework after this, after my session, is to go away and find out why Jane Jacobs did not like what Patrick Geddes did, although they were really, singing from the same hymn sheet in that sense. Okay, now I could revisit many of these partial and incomplete theories over and over again, and we could spend the rest of the morning, the rest of the sessions talking about them. But this gives you a pointed idea in terms of what theory was all about, and the relative rudimentary nature of theory, the fact we have many theories in that sense. Now, the physical dilemma that I call in this sense is that a good deal of our thinking about cities is in terms of manipulating them, making them better through changing their physical form in this particular context. Most of our planning really manipulates cities in a deterministic way by changing form, rather than function, although function to some extent is being changed. But function in terms of human behavior is not really the prerogative of urban planning in that sense. So the great dilemma is that the physical dilemma is that how do we reconcile physical change in cities with changes in social behavior? In fact, Wei Yang and myself, she was the president of the RTPI last year, set up a task force in the UK to look at methods in planning. And we found, in fact, there's the link there to our task force report, please download it. We found, in fact, that in British planning, most of the techniques and tools, although we're being informed by digital thinking and informed to a very limited extent by a science of cities, were relatively modest and small scale. Much of the big scale thinking in terms of the science of cities is barely applied in a practical context, and thereby hangs a tail in this particular context. It's difficult, if not almost impossible, to develop large-scale modeling and large-scale thinking because it's exhaustive, it takes time, it's costly, and so on. We often don't have the skills or the data in that sense, and that's one of the crosses that we have to bear in terms of developing this science. Okay, so in some respects, the ideas that we've got at the present time are still being represented physically. So the grand challenges that face our cities, climate change, aging, energy, and so on, are all basically issues that we can think about, or we are thinking about in terms of physical change in that sense. Okay, let me say something about ideal and real cities. I've said something about this already. I've shown you the picture of Corb, basically, Corbusier in that sense. I'd also like to say that in terms of theories about ideal cities, then what we really got to accept is that ideal cities are visions. They're always wrong. George Box, the statistician, has a famous phrase, all models are wrong, but some are useful. We ought to wear that on our arm, basically, in a sense, if we're involved in modeling. All models are wrong, but some are useful. We can actually say that about theories. We can say it about all sorts of things that relate to planning. All theories are wrong, but some, maybe all of them in different ways, are useful. Ideal cities are wrong. We can't really build them in any senses, I'll show you in a moment. But at the same time, they're useful in terms of thinking about how we can head towards things that are visionary in this particular context. Here are some pictures of ideal cities. You can see Brasilia on the left-hand side. I'm not going to go through these, basically. If you want to look at them, then please download the PDF. But you can see a whole variety of forms. What this collage really shows you, the top lines of those cities are ideal cities, and the bottom are sort of real cities in some sense. That's London at the bottom there. What you're seeing in this particular context is that there are many, many different morphologies. It's not surprising that planning is related to morphology, the morphology of cities. In Singapore, for example, you have particular morphologies in terms of neighborhoods and districts and so on, which have been implemented over many years, basically very different from what's north of Singapore in southern Malaysia and so on in that sense. Let me show you that this is a real city, etc. The bottom line are real cities. The top lines are visionary cities or ideal cities. And let me also show you the last picture in that sense is indeed Singapore at the tip of Malaysia there, and also Indonesia. Let me blow it up in a sense and make a couple of comments. Clearly, you can see Singapore quite clearly there, and you can also see and probably work out intuitively that the form of urban development on the north and the south of the Singapore island is rather different from Singapore itself. Were we to measure the statistical morphology, using statistics, the morphology of these clusters in that sense, we'd find using something like fractal dimension, for example, which is quite well known in this field, then you would find that the Malaysian development was a bit more sprawling. It was a bit more sort of spread out, really. The Singapore development is more compact. So we could make a measurement in this sense. So even though we may not be completely convinced that physical planning is the ultimate aim of changing cities in some sense, we do see that planning makes a difference in this particular context. Okay, well, when we look at these cities, what we find, in fact, is that both in real and ideal cities, at different scales, there is similarity. The principles of central place theory are that in cities we have a small number of big things and a large number of little things, and we have hierarchies that link them together. You can see this in terms of shopping centres, transportation routes, sizes of housing, sizes of various neighborhood centers and so on. You can see all of this in sense. And the real trick, of course, is to use these ideas, which are going to be elaborated during this symposium, to use these ideas to actually think about how we can actually begin to plan complex systems in that sense. What I should say is that one of the key messages in my talk this morning is to say to you, in a way, the models that we develop in urban science are not necessarily models that can actually give us good predictions or good prescriptions. They're models that we can use to actually figure out how good our intuitive predictions about what the future might be. So to some extent, they're tools to actually probe how good our plans are rather than to actually generate plans themselves. I'll come back to that point in a moment. Okay, so let me just show you the classic example in the British context of a real city and a visionary city. So this is London, and London, the morphology has not changed much over the last 300 or 400 years in that sense. It's grown, and you can see the little towns, or the big towns, I should say, in the periphery. There's probably about 15, no, maybe 20 million people in that area. The Greater London area is the sort of central bit, basically. And of course, on the right, you see Ebenezer Howard's famous garden cities, the new towns being taking purely the industrial the industrial grime and soot and so on and pollution away from the central city. And you can also see, were I to map the Ebenezer Howard on the diagram on the right onto London on the left, you could see a number of those towns in the periphery are in fact the British new towns, places like Harlow, Stevenage, and so on in that sense. So you can see that this is perhaps the closest the vision ever got to the actual reality in some sense. Okay, rudimentary models of city systems. Very conscious of time here. Let me go through this very quickly. There are two sorts of models out there. One are aggregate models, which enable us to actually look at long-term change in population, employment, lots of other activities, and so on. The other are more shorter-term models to some extent, more disaggregate models leading to development processes. We call the first ones aggregate static models, basically geodemographic models in that sense, spatial interaction. And the second class are things like agent-based cellular automata. So the difference here is, to some extent, scale, but it's also the way we actually represent the system, either as aggregates or indeed as individuals and agents in that sense. And that really is the sort of development of modeling over the last 50 years or so in this particular context. Many of these ideas have sort of hit a brick wall to some extent, that there are limits to how far we can go with these models. So aggregate models were found wanting in the 60s, and more disaggregate cellular automata then emerged, basically focusing on rather different things, the development process, and then more agent-based generic approaches have emerged since then, such as the large-scale transportation models such as NatSim and TransSim and so on and so forth, sim mobility. Okay, so let me have a quick look at one of these models. Here's a very typical notion about some activity A relating to some activity B. We might think of employment and population, and we might think of those links as being movements or links between them in a sense. We can also have an economic version of that, where employment flowing from workplace to house to residential and back to workplace in that sense is paralleled by wages at workplace and revenues being used to actually move people around, transport costs, to buy houses, house prices, and so on in this context. So you have both a physical and an economic version of these land use transportation interaction or LUTI models, these aggregate models in this particular context. Now, what I'm actually going to do, in fact, is to take this model structure, which is an equilibrium model structure, and use it to actually probe scenarios to see how good the ideal city is by taking this model and actually tuning it to some extent to an ideal situation and indeed to real situations, and just showing how far we can get. What I will demonstrate is that the ideal model is non-workable in terms of the equilibrium assumptions which are contained in this particular model. And I'll show that. So let me move on, in fact. I should say a little bit more about cellular automata models, how the cities spread. We're not going to use those to actually probe scenarios in any sense, but they can be. This is a picture of Cardiff, where I worked in the 1980s. You can see the development of the city on Cardiff Bay and the Severn Estuary. And then you can see a couple of examples of how we can grow cities using cellular automata and fractals and so on, really from the bottom up. So you can sort of see in the left and the middle pictures how we've planted a kind of a seed, if you like, and let it grow within the container, the physical container, which is Cardiff. And then on the immediate right, we have the classic fractal diffusion limited aggregation. So I'm not going to go into that anymore, but it's quite an important part of urban science. Okay, the systems approach in some sense and complexity theory. Let me quickly say that if you want a good introduction to complexity theory, in this context, I should just say that systems theory, top-down thinking, from where we thought about the city as a machine, gave way in the last 30 years or more to complexity theory, where we think of cities from the bottom up, growing from the bottom up, and to some extent, which is more consistent with, you know, how individuals relate to cities in this particular context. We should also make the point that both of these approaches to some extent are being complemented by the development of ideas about data driving cities in that sense. Chris Anderson's article, Wired in 2010, where he says that we called it the end of theory, basically said that really everything we need to know is in the data, in big data in some sense. Now, I don't believe this for 1 minute. I don't think we can face the world without theory. And we do have a large cornucopia of theory, which I've hinted at here in some sense. And I don't believe the world is as ad hoc as the data scientists would have us believe in that sense. So although we're in the era of artificial intelligence in that sense and big data, I think there's some very profound limits in terms of the future, which really pertain to that. It's another discussion. Predictability or other unpredictability is really all about this to some extent. Okay, so if you want to have a quick look at the origins of complexity theory, which really back all of this up, then there's a picture of Jane Jacobs' book from the early 1960s. It's not the copy I had when I was a student, basically, although it was probably about the same price, 8 and 6pence in the old British money. Science and Complexity, Warren Weaver's paper and Herbert Simon's paper are great reading. So indeed is The City is Not a Tree, from the great Christopher Alexander in that sense. And I should say, if you want to have a quick summary of some of these things, my own book, Cities and Complexity, in 2005, and my more recent book, The New Science of Cities, not that recent, 10 years now, basically. But these actually contain a lot of those ideas that I've just been alluding to. Okay, why ideal cities don't work and will never work, basically. I've said that if we take a model structure of the kind I've alluded to, in a sense, how things relate to each other and so on, geodemographically and in terms of spatial interaction, and we apply it to cities like this, we ask the question, to what extent can a city which is built on a line, and this is Neom, to what extent, if people are given free rein, basically, and behave in the way that we know people behave in cities in terms of the impact of distance and travel time and rent and so on, how will the city actually emerge in that sense? How close is it? Will it begin to spread out? A bit like Brasilia. Brasilia was built on this idea of an aeroplane or a wing, 2 massive wings, linear wings. And of course, if you now look at Brasilia 50 or 70 years on from when it was originally planned, then you can see that the sprawl and the normal urban development that we see in most cities has really filled it all in. And the visionary thing, okay, it's still there to some extent, but essentially it was very hard to maintain. Okay, what we've done in this context, and I'll quickly go over this, we've got a city on a line, so the the top little square basically is our space, and we have the city on the line. And what we actually do is we have a model which enables us to actually look at each individual point in this sense, each individual neighborhood or person or however you want to see that representation, and shifts it to higher accessibility. So the model is actually moving people to become more accessible. And as you might expect, in a world where the easiest way of thinking about people being related to one another is in a cluster, in a circle in some sense, a line moves very quickly to a kind of circular form. And the paper that we did on this simply demonstrated that simple idea that if we start off with something out of equilibrium, as far as a line is in a sense, and we apply some equilibrium assumptions about gravitation, accessibility, and so on, then what we end up with is a circular system. So here's another picture of this. There are lots of different variants of this. And of course, we can say, you might say, well, this is all very obvious, really, in a sense, but at the same time, we can actually tweak it in different ways and explore some interesting variants, basically, to the extent to which how integral, how stable is the line under different sorts of configuration. Okay, and there's the paper that was a couple of years ago where I looked at the logic of this sort of spatial equilibrium. Okay, complexity to explore real cities. Now, I'm going to go over this very quickly and just mention it. There are a couple of examples here that you can look at your leisure if you want to get the PDF. We've done something in Singapore with the people at A*. This was about 7 or 8 years ago, basically. There's a paper in +1 showing you how we can actually spread using a cellular automata-like model, but there's lots of things in those models in that paper that pertain to things that go on in Singapore, the Singapore Master Plan and that sort of thing, as well as constraints and so on. So have a look at that. And then there's another model, an agent-based model of the growth of Suzhou in the Shanghai Nanjing area, basically, in that part of the world, and that's in the annals of the American Association of American Geographers, basically. So that's an agent-based model in this particular context. Now, to some extent, this talk has been an informal chat about models, basically. And I've really been making the point we have many models, often of the same system. And in the current parlance, we call these digital twins. It's a term that's increasingly being used. It's highly evocative because can we have more than one twin? Can we have triplets, quadruplets, and so on? Can we have identical twins, non-identical twins, and so on? But a twin is a model, basically, in that sense. And we've moved into this multi-paradigmatic world, basically, where we have many theories, many models, and so on, largely because we have many new ways of computation in some senses. And all of us have slightly different views about the world and about cities in this sense. And all of this is really contained in this notion that we can have more than one model, basically. And there are many models, of course, which can't be formalized in any strict scientific sense or any mathematical sense, basically. And of course, these are really also candidates. They're non-digital twins in this sense, and they're important in terms of our thinking. I've talked about digital twins. I talked about digital twins, I think, with Lewis in the NUS Cities program when we came a couple of months or so ago, when we were both physically present in Singapore. And in some senses, I don't want to really repeat this. All I want to say is that the digital twin idea, the many model idea, the many theory is quite an important element in terms of my particular thinking about how urban science should develop in that sense. So let me say the future digital world will be composed of many twins, basically. As everything around us becomes digital, or rather infused with digital interactions, then we'll face a world of many models and many twins. We need new strategies for dealing with the multiplicity of ideas and for integrating them in ways that exploit their relevance. Now, I've not broached the idea of the smart city much in this talk. A lot of our cities are turning into computers, basically, in the sense that not the infrastructure we're developing in terms of models is gradually being incorporated into the infrastructure of the city, in this sense that None of that is very surprising in some senses, that we see it classically in terms of things like building information model systems. A building is actually built using a design model in some sense. The design model is then used to assemble the building in some sense, it's a construction, and then really becomes part of the building in terms of its maintenance. And in many senses, the sort of models that we have here, although that's a rather grandiose sort of aim in some sense, the models we have here could well be on the same path to be integrated into our planning agencies. So one of the key things too is that this sort of science needs to be integrated into the planning agencies at every stage. In that sense, it needs to become part of the furniture. Computers to predict computers, that's really what all of this is about. And to some extent, we've got to factor in things like artificial intelligence and so on in terms of our plans for future cities. Now, I hope this seminar will advance these ideas, and I look forward to the discussion. Hope I haven't gone on too long. Thank you very much for listening. There again is the place where you can get the PDF, usw.pdf from my blog, basically. So again, if you want to do that, it's easy enough to do. I should also mention that at the end of this series of talks, basically, which we've kicked off today, then the Urban Solutions and Sustainability Congress on the 4th and the 5th of November really sort of finalizes and pulls together many of these ideas that we're talking about here. I should also reference a couple of things you could look at. The role of complexity for digital twins of cities. That's the paper that some of us wrote on complexity and the idea of many models in some sense in Nature Computational Science. And there's the translations of a couple of my own books. And last but not least, the book on urban informatics that you can download at your leisure because it's free. I know Lewis has an article in there, and I'm one of the editors, and there are probably other people speaking at this meeting who have material in that. Okay, thank you very much. I'm going to stop sharing, and then I will be sending the MPEG movie to you, basically, at that point. Okay, I'm going to stop recording at this point. Okay.